Hey guys, Mrs. Bodechon here. So we are going to continue with AKS Portfolio 1A, and we're going to be discussing isotopes and ions in this one, okay? So the very next thing on your portfolio asks you all about isotopes and all of these crazy questions. So let's get into actually what is an isotope first, okay? So an isotope, let me move myself over, is an atom that has different forms, different forms of an element that has the same number of protons, but different number of neutrons. So if you look at this example here, we can look on the periodic table to see what element this is. It's telling us there's 8 protons. So if I go to the periodic table and I look for number 8, because remember, the atomic number is how many protons are in my element, this would be oxygen. So if I'm looking at this, these are two different forms of oxygen. They have the same number of protons, which means they're the same element, oxygen. But what's different about them is their number of neutrons. So this one has 8 neutrons and this one has 10 neutrons. Because they are a different number of neutrons, we call them isotopes of each other, okay? So same protons, different neutrons is an isotope. So what does this really affect in an atom? It doesn't affect the charge because neutrons are neutral, right? So it doesn't make it more positive or more negative. It's still staying neutral. But what this does affect is the mass, because neutrons, as you probably remember, have a mass of 1 AMU, 1 atomic mass unit. So if we have more or less neutrons, we're affecting the mass of our atom, which is why sometimes you'll see on the periodic table for the atomic mass numbers at the bottom that they're decimal points, right? And that's because there's different naturally occurring isotopes for each element. So what scientists do is they collect how many of each one are in existence, right? And then they average them together. So this is an average of the mass for carbon, for every carbon isotope that exists that we know about, right? That's why it's a decimal, because you can't have part of a neutron. That's impossible, right? So they just take the average of what's naturally occurring. Okay, so this says name the isotopes in the model. So how you name an isotope is you write the full name out. So oxygen. Then you put a dash. Then you're going to put the atomic mass at the end. Now it's the atomic mass of that particular atom, okay, not the atomic mass off the periodic table. So for this one right here, we're going to count up the protons plus our neutrons because that's where we find our mass. Remember, electrons are so small they don't really count for mass. So just do protons plus neutrons, so that gives us 16, 8 plus 8. So we write oxygen dash 16. And that way I know this isotope has a mass of 16, so I can figure out the neutrons of this particular atom because mass minus protons gives you neutrons, okay? Now this atom right here has 8 protons and 10 neutrons. If I add those two up, 8 plus 10, it gives me 18. So I would write it oxygen dash 18. And the 18 signifies the atomic mass for that particular isotope of oxygen. It says, for number 3, write the nuclear isotope notation for both. Well, that is already written down here at the bottom, and it's super simple. The notation for it, you're just going to write the symbol of your element, so a capital O. And then in the upper left-hand corner, it's going to be a superscript, okay? You're writing the same number, which is the atomic mass. That's it. So it's a capital O and the 16, or a capital O and the 18. Make sure it is in the upper left-hand corner, though, because it is a superscript. All right, so let's talk about ions. Ions are completely different, right, than isotopes. So what an ion is, and this is what your paper is asking you, but let's really talk about for a second what is an ion. An ion is a charged atom. So it's either going to be positively charged or negatively charged. And if it's positively charged, we call it a cation. And if it's negatively charged, we call it an anion. So let's talk for a second about how we can make an atom charged. Atoms are not going to lose protons, okay? They're not going to lose or gain protons. So when we're discussing ions, we're only talking about losing and gaining electrons only, all right? So if an atom gains electrons, electrons are negative. So if I'm gaining electrons, I'm gaining negativity, so I'm becoming an anion, all right? On the other hand, if I'm losing my electrons, I'm giving them up, okay? If I'm losing this negativity, I'm becoming more positive, so I'm going to be a cation. So let's look at these examples. This one says, define, is it a cation or an anion? What tends to form more? So let's look at our periodic table and see how this goes. So here's a periodic table. And you can find the number of electrons in the outermost shell. That is what we're really after here. We're not really after the total number of electrons when we talk about ions. We're after our valence electrons, which is the ones in our last shell. It's a valence shell, so we call them valence electrons, the outermost shell. And we're going to use the group number for that on the periodic table. So if you look at this top number, it says 1, 2, we're going to skip a few. We're not going to work with the transition metals, but we are going to start right here with the boron family for number 13, 14, 15, 16, 17, and 18, okay? Now these numbers are the group numbers, and they represent how many electrons are in the valence shell. So everything in this column is a family, okay? And this is going to be one valence electron. These are going to have 2 valence electrons. I'm going to skip a few and go over here to 13. Now, we know we can't fit 13 electrons in our shells, right? We can go 2, 8, and then 8, and that's it for our class. So what we're doing is we're going to cover up that 1 in front of the 13. And we're going to say, okay, there's 3 valence electrons here. And this one, instead of 14, there's 4 valence electrons. We're going to cover up that 1. So this one has 5, 6, 7, and then 8 valence electrons, okay? There's a couple exceptions to that rule. We'll get into that a little later. So let's go ahead and look at our example. Ions. So we have sodium. Sodium is Na, and sodium is right here in column 1. This is our group 1, right? So therefore it has 1 valence electron. So if you look at our Bohr model, they went ahead and they drew it, and it does indeed have 1 valence electron here. But all atoms really want to have a full octet. And a full octet is a full outermost shell. So their valence shell being full with 8 electrons, it makes them stable. It makes them like happy, right? So that's what all atoms are after. And they're going to get there in the quickest and easiest way possible with using the least amount of energy. Now, when sodium does that, it would be really difficult to go around and get 7 electrons added to this atom to make it 8 valence electrons on the outer shell. So instead, what sodium does, since it only has 1, is it gives that one away. It's like, there you go, that's not a lot of energy for me to give this electron away. And then this outermost shell has no electrons on it, so it just disappears, okay? It kind of vanishes. And then we're left with our full octet underneath. Now sodium is stable, it's happy, okay? So when we did that, when we lost 1 electron, it will become positively charged by 1, okay? We lost a negative, now we're positive by 1. The opposite occurs in chlorine. Chlorine, you can see, has 7 valence electrons. We're over here, and chlorine is right here. So it's in group 17, so we have 7 valence electrons. Remember, we cover up that 1. So what's going to happen in order for chlorine to have a full octet is it's not going to give away 7. That's a lot of energy, right? Instead, it's going to go and it's going to take 1. So chlorine is going to take 1, giving itself a full octet. Because it took a negative electron in, it's now charged by a -1 charge, okay? So this is an anion, and this is a cation. Now, if we look at the periodic table, you can see that metals tend to form cations and nonmetals tend to form anions because of their give and their take, okay? So metals forming cations are metals. Our metals are mostly on this side, right? So if we have lower numbers, 1 and 2, and a little bit over here with 3, we're going to be giving those away because those are lower numbers. It's much easier to give a lower number away than to take a big number, right? So because they're giving them away, we end up more positive. So all metals tend to form cations. On the other hand, our nonmetals are over here on the periodic table, and they're bigger numbers, right? 6, 7, 8. So it's much easier for them to collect a few rather than to give a lot. So they're going to end up taking a few negatives in, a few electrons in, becoming more negatively charged. So they are typically anions. Okay. So let's look at some examples of what ion notation looks like. So here we have an ion. This is lithium +1. And it says how many protons, how many electrons, like give me all this information, right? So we need to first go to the periodic table. Lithium is right here, it's number 3, and if you notice, it's in group 1, all right? So oh, I even put a little picture here for you guys. Let's see if I can move this. That's okay. All right, so first, how many protons? It's number 3, so therefore it has 3 protons. How many electrons does it have? Well, in a neutral atom, it would have 3 to counteract those 3 protons. 3 protons, 3 electrons. However, this is saying it's positively 1 charge, so we had to give 1 away, right? We're in group 1, so it's going to give 1 away, leaving it with only 2 electrons. So it becomes a cation by +1, okay? It's a cation by +1. It gave 1 electron away, so it does indeed become a cation. So here's the model. You can see it started off with 3 electrons, and it really wants a full octet. Now this one's unique because lithium has only 3 electrons. So if it gives that one away, which is going to be the least amount of energy for it, so it definitely will, it's not left with a full octet. It's left with a full like duo, right? It only has 2. But that first shell can only hold 2. It can't hold 8. So it's still stable. It's still happy because it has a full outer shell, okay? Let's look at one more example. Fluorine, -1. So if we look over here, here's fluorine. It's number 9, and it's in group 17. So if we look at this, we can see that because it's number 9, it does have 9 protons. And a neutral atom, it would have 9 electrons. However, this is -1, which means it had to gain 1 electron, right, to become negatively charged by 1, which makes it have 10 electrons now, and that becomes an anion. So here's your model. You started off with 9 electrons total. So 2 and then 1, 2, 3, 4, 5, 6, 7. We really want 8. We really want that full octet. So what does it do? It goes and it gains 1 electron right here to have a full completed octet. All right, guys, ask me if you have any questions.